Hi again. In this lecture, we will solve a couple of examples which are based on the concept that we've just learned in previous lectures. The concepts of axial stress, axial strain, and elongation of short, straight, axially loaded bars. So let's begin with the first example, in which a straight bar AB having a length of 3.5 meters and the bar is subjected to an axial force P, which has a magnitude of 200 kilonewtons. Now, if we were to cut the bar and look at its cross section, say for example cross section XX, the bar will have a rectangular hollow cross section as shown in this diagram. And I will just hatch the walls of the cross section in order to indicate that there is where the material was cut, and so one can easily see that the cross section is hollow, empty inside. The size of the section is 152 millimeters along the long side, 102 millimeters along the shorter side, and the wall thickness all around the section is 9.5 millimeters. The bar has the same cross section throughout. From A to B, the cross section is constant. One would have to determine, firstly, what is the axial stress in this bar, and secondly, what is the elongation of the bar if the bar is made of steel with a modulus of elasticity of 200,000 megapascals. Now, as a note, 200,000 megapascals is a typical value for the modulus of elasticity for steels. So it's a number that you might want to remember. So let's address the first question. We all remember that the axial stress equals to the axial force divided by the cross-sectional area, in which we need to determine the cross-sectional area, and we can do so in several ways. What I decided to do here is to calculate the area of the outside rectangle and subtract from it the area of the inside rectangle, which is a hole really, and the result is 4,465 millimeters square. All we have to do now is divide the force expressed in newtons by the cross-sectional area expressed in millimeters square to obtain units of newtons per millimeter square of megapascals for the stress, and that would amount to a positive 44.8 megapascals, which is a tensile stress. For the elongation now, that is equal to PL over EA, and all we have to do now again is plug in the numbers, paying careful attention to the units to be consistent. So we can see newtons for the force, millimeters for the length of the member, megapascals or newtons per millimeter square for the modulus of elasticity, and millimeters square for the cross-sectional area. The result of this is positive 0.78 millimeters, which indicates that bar AB becomes longer by that amount a positive elongation, big bar becomes longer. It corresponds to a positive axial stress for, or the result of the tensile force applied to this member. Now, let's continue with a second example in which this time we will consider a column, a steel column, which is 4 meters tall and has a circular hollow cross section, as I will show shortly in a simple diagram. Now, a column will always be in compression because of the forces that, the gravity forces that act on the column from above. One would have to determine the axial stress and the elongation of the column, similar to the previous problem, if the magnitude of the axial force is 150 kilonewtons. Again, the modulus of elasticity for the material, for steel in this case, is equal to 200,000 megapascals, which, as I just mentioned earlier, is a typical value for structural steel. Now let's look at this cross section quickly. As I mentioned, it's a hollow circular section, and this column has an external diameter of 101.6 millimeters and a wall thickness equal to 5.74 millimeters. And of course, like in the previous problem, the cross section of this column is constant. It does not change along the 4 meter length of the column. So, first question requires us to determine the axial stress in the column, which is equal to P over A. And if we plug in the numbers, we will note that we need to determine again the cross-sectional area first, and I will calculate this area in the same manner as before, namely subtracting the area of the hole from the area of the outside circle, and that would give us a value of 1,730 millimeters squared. Plugging in the numbers in the formula for the stress will give us, by paying attention again to the units, a negative force divided by the cross-sectional area, and of course the negative force is because the column is in compression. So hence the stress, the resulting stress, will be equal to negative 86.7 megapascals, and the negative sign indicates that this is a compressive stress in the column. For the second question, we need to calculate the elongation of the column, and of course you can imagine that the column being under compression, the elongation will be shortening of the column. Again, please pay attention to the sign of the applied compressive force, which is negative, and also please pay attention to the units, which must be consistent in order to obtain meaningful results. The elongation will result as negative 1.73 millimeters. So the negative sign indicates that this column will indeed become shorter as a result of the compressive axial force that is applied to this column. So these have been a couple of very simple example questions. I thank you very much for attending this lecture, and I will welcome you at the next ones where we'll discuss in more detail on how to design members under axial force.